Welcome to DI Paper Podcasts. Today we are doing a deep dive into a paper called Perceptive Humanoid Parkour Chaining Dynamic Human Skills via Motion Matching.
And we are jumping right in because the results on this one are honestly wild.
Yeah, they are. So here is the headline for the short form edit. We are looking at a Unitree G1 humanoid. It's about 1.3 meters tall, performing autonomous parkour.
Right, it's cat vaulting over obstacles at 3 meters per second.
And scaling walls up to 1.25 meters high, which is
96% of its own height.
exactly.
Yeah.
And the core mechanism here is that they completely moved away from pure end-to-end reinforcement learning.
Or even simple reward shaping. Instead, they built this modular framework they call PHP.
Perceptive Humanoid Parkour, which uses two key pieces of tech. First, motion matching.
Which is actually a technique ripped straight from video game animation. They use it to stitch sparse human motion data into these long, fluid reference trajectories.
And second, hybrid distillation. So they train privileged teacher policies via RL and then distill them down into a single vision-based student policy.
But using a combination of DAgger, which is imitation learning, and PPO, reinforcement learning.
The result being a successful zero-shot sim-to-real transfer where the robot autonomously chains skills like running, jumping, climbing, and rolling.
Using only its onboard depth sensors.
All right, so that is the short-form summary. Now let's really unpack this because, as you know, seeing robots do parkour isn't entirely new. Boston Dynamics has had Atlas doing backflips for a while.
Sure.
So why is this specific paper such a big deal for the ML and robotics community right now?
It really comes down to the agility gap. If you look at most humanoid locomotion papers out there right now, or even the commercial bots that are hitting the market, the focus is almost entirely on robustness.
Meaning the goal is basically just don't fall down.
Right. You want to walk over rough terrain, maybe get over some stairs. It's a static stability problem. You're
Yeah.
trying to keep the robot's center of mass safely within its support polygon.
Like balancing a broom on your hand.
Yeah.
Just keeping it upright.
Exactly. But parkour is a completely different beast. It requires high-dimensional whole-body control.
Using both arms and legs.
Yeah, and you are often intentionally throwing your center of mass way outside of your support polygon just to generate momentum.
You have to fully commit.
You do. But the hardest part, and this is the specific bottleneck this paper targets, isn't the jump itself. It's skill chaining.
Skill chaining.
Yeah.
So the problem isn't just getting over the box.
No, in isolation, we can train a robot to jump. The real problem is that in the real world, you don't just spawn in front of a wall, jump, and then the episode ends.
Right.
You have to run up to it, spot the obstacle, adjust your stride, transition into the vault, land, and then this is the absolute killer. You have to instantly transition back into a running gait.
To keep your momentum going.
Exactly. If you mess up that transition, you fall over.
Yeah.
Or you just lose all your kinetic energy and stop dead.
So the transition is the failure point.
We actually call it the valley of death in locomotion. You can have a perfect running policy and a perfect vaulting policy.
Yeah.
But if the robot lands and doesn't know how to resolve that high-impact landing state back into a run,
Whole system crashes. Which I guess brings us to the data problem. Because to train a neural net to handle those transitions, you would need a massive data set of continuous chained parkour moves.
which we do not have for robots.
We rarely have it for humans.
Exactly. Finding high-dynamic human motion data is incredibly hard. You might find a mocap clip of a stuntman doing a perfectly executed cat vault, but
But the clip is, what, maybe 2 seconds long?
if you're lucky.
Uh-huh.
And it doesn't include the 10 seconds of running before the vault, or the approach from different weird angles, or the recovery.
Right.
And trying to train a long horizon policy on those tiny isolated snippets is notoriously awful because the network just overfits to those specific frames.
Okay, so they have a puzzle, but they are missing half the pieces. And this is where their first major technical contribution comes in, motion matching. Which, I mean, anyone who plays games like Assassin's Creed or FIFA will recognize this. This is literally how game characters move.
It is the exact same concept, just adapted for robotics. In a video game, when you push the analog stick forward, the game engine isn't calculating simulated muscle physics from scratch every single frame.
That would cook the processor.
Right, it would be computationally insane. Instead, the engine searches a database of pre-recorded animations.
It's doing a nearest neighbor search.
Exactly. It looks at the character's current pose, their current velocity, and the user's desired future trajectory based on the joystick. And then it scans the database, finds the mocap frame that's the best match, and stitches it in.
And so this paper applies that exact logic to the robot's reference generation.
Yes. Instead of asking a neural net to just hallucinate a reference trajectory from scratch, which usually leads to weird, physically impossible movements, the system searches a database of real human mocap frames.
It's basically retrieval augmented generation, but for physical motion control.
That is a perfect way to describe it. It retrieves a physically valid human motion plan. And this is how they solve that data scarcity problem, using a process they call densification.
I found this part so clever. Walk us through densification.
So imagine you only have that one single mocap clip of a human vaulting a box. In the raw data, the human approaches from exactly 2 meters away, leading with their right foot.
But in the real world, the robot might be 3 meters away, or 2.5.
Right. Or it might be stepping with its left foot. The stride phase could be totally out of sync with the original clip.
So the raw clip is useless on its own.
Exactly. But motion matching allows the researchers to artificially densify the data. They can generate thousands of valid simulated trajectories. They have the robot approach the wall from every possible distance, angle, and foot phase.
And the system just finds the right frames to bridge the gap,
It automatically fills in the missing frames to connect the run to the jump.
turning a tiny bit of data into this massive ocean of training scenarios.
And they structure it in a very specific way. They treat basic locomotion just running as the universal connector. So the sequence always goes. Locomotion, transition to atomic parkour skill, transition back to locomotion.
Like the bread of a sandwich.
Right. But there's a catch here. When you stitch two totally different motion clips together, like cutting from a sprint into a vault, there's usually a harsh cut or a jerk where the poses don't perfectly align.
Which, if you are a robot moving at 3 meters per second.
It's catastrophic. It completely destabilizes the hardware.
So how do they fix the jerk?
They use another animation technique called inertialization. It's essentially a smoothing algorithm. It computes the offset between the current motion and the target motion, and then decays that offset over time.
So it blends the physics.
Exactly. It makes sure the robot doesn't aggressively shudder when it switches from running mode to vaulting mode.
Okay, so now we have these beautiful, dense, stitched together reference trajectories, but the robot can't just play them like an MP4 file.
No, it has to physically execute those joint angles against gravity, friction, and its own motor limits.
Which brings us to the training pipeline. And honestly, this was the most fascinating part of the paper for me.
The teacher-student model.
Yeah. Now, teacher-student distillation is standard in robotics, but they added some really specific tweaks for parkour. Let's break down stage 1, the teachers.
Right, so the teachers are these privileged expert policies running in simulation.
And privileged here basically means they are cheating.
100%. The teacher policy has God mode enabled. It knows the exact friction coefficient of the ground, the exact mass of the robot, and crucially, it knows the exact height, depth, and position of the obstacle.
It doesn't have to guess.
Right. And they train individual expert policies for each distinct skill. So there's one expert just for vaulting, one expert for climbing, one for dropping.
And they mentioned a specific detail during this stage adaptive sampling. They said without adaptive sampling, the robot couldn't learn to climb the 1.25 meter wall at all. Why is that?
Well, the high wall is simply the hardest task in the set. If you use uniform sampling, meaning you just randomize the tasks evenly during training, the robot spends most of its time practicing running or jumping over small boxes.
Because those are way easier and they show up more frequently.
Exactly. It rarely attempts the massive wall. And when it does attempt it, it fails immediately.
So the neural net never gets enough gradient signal to actually learn the climbing mechanics.
Right. So adaptive sampling forces the system to pay attention to its own failure rates. The system realizes, oh, I have a 0% success rate on this 1.25 meter wall. So it dynamically cranks up the probability of that specific task appearing.
It forces the robot to grind the level it's stuck on.
Exactly. It forces it to practice the thing it sucks at until the policy converges.
Practice makes perfect. Okay, so we have fully trained God mode teachers. Stage 2 is the student. This is the policy that actually deploys on the real hardware.
And the student does not get God mode.
No. It only gets a depth camera and its own internal joint sensors. Proprioception.
Right. And this is where the researchers ran into a really fascinating failure mode. The standard industry approach to distill a teacher into a student is DAgger, dataset aggregation.
Which is imitation learning.
Yes. The student just tries to mimic the teacher's actions as closely as possible. But they found that DAgger alone completely failed on the high dynamic parkour skill.
Really? Because DAgger is practically the default for this kind of thing. Why did it fail?
It failed because of something they dubbed the torque burst problem.
The torque burst. Sounds like a special move in Street Fighter.
It basically is. Think about climbing a wall that is as tall as you are. You run up, grab the top edge, and then you need this one massive explosive pull to get your entire torso up and over.
Yeah, you have to rip yourself upward.
That action requires a huge instantaneous spike of motor torque for just a fraction of a second.
You can't half measure it.
But DAgger uses an L2 loss function. It's trying to minimize the average error between the student's output and the teacher's output over time.
Oh, I see where this is going.
Right, so if the student generates, say, 90% of the torque the teacher used, mathematically the error is pretty small. The L2 loss looks at that and says, good job, you're close.
But in reality, 90% of the torque means you slam into the wall and fall backwards.
Exactly. Because the loss function is averaging things out, it naturally penalizes the massive, risky spikes in torque. It smooths out the peaks.
It's regression to the mean, but applied to extreme athletics.
That's a great way to put it. The student learned to be conservative. It would run up, reach for the wall, mimic the general shape of the movement, but it just wouldn't pull hard enough because it was trying to minimize variance instead of actually completing the task.
So playing it safe guaranteed that it failed. How did they actually fix that?
They fixed it by mixing DAgger with PPO, proximal policy optimization.
Which is standard reinforcement learning. It uses a reward function instead of just pure imitation.
Right, so they added a task-level RL reward during the distillation phase.
So DAgger's saying, look exactly like the human reference, and PPO saying, I don't care what you look like, just get your center of mass over this wall.
Bingo. By combining them, DAgger keeps the motion looking natural, so the robot doesn't start flailing its arms wildly or exploiting physics glitches in the sim, while PPO forces the robot to actually succeed.
It specifically incentivizes those high torque bursts.
Yes, PPO pushes through the smoothing effect of the imitation loss. It rewards the explosive power needed to clear the obstacle.
That is such an elegant fix. It solves that inherent averaging problem in imitation learning. I honestly wouldn't be surprised if this hybrid distillation and mixing imitation with a task reward becomes the new standard for dynamic robotics.
I agree. I think we'll see a lot more of it.
Let's shift gears and talk about perception. Because for any of this to work, the robot has to actually see the obstacles in front of it. And you mentioned the student policy only uses a depth camera.
Yes, an onboard depth camera running at 30 Hertz.
But the robot is moving at 3 meters per second. The lag must be an absolute nightmare.
Lag is the enemy of agility. When you're running that fast, by the time your computer processes a frame, you've already moved half a meter forward. The world has changed.
So how did they cross the sim-to-real gap with that much latency?
They had to get very aggressive with domain randomization during training.
Now, normally that means randomizing floor friction, maybe the weight of the robot links.
They did that, but it wasn't enough. They also heavily randomized the camera extrinsics.
Meaning the physical position and rotation of the camera itself.
Right, because on a real physical robot doing parkour, the camera mount might vibrate, or it might be installed a millimeter off-center. But the most critical thing they randomized was the latency itself.
Latency simulation.
They simulated observation delays, randomly fluctuating between 60 milliseconds and 80 milliseconds.
So they essentially train the policy to predict the future. The robot sees a depth image of a wall, but it inherently knows that by the time its motor commands actually fire, it's going to be closer to the wall than the image suggests.
Exactly. It learns to act on where the wall will be, not where it was 80 milliseconds ago.
There was also a really specific note in the perception section about depth noise that caught my eye. They added realistic sensor noise, but they explicitly excluded Gaussian blur.
Yes.
Why? Usually in computer vision, you add blur to make the model more robust to bad lighting or fast movement.
You do, but it turns out that at these speeds, Gaussian blur is actively harmful. Gaussian blur softens the entire image uniformly, and when you soften the sharp edge of a 1.25-meter wall, the robot can no longer accurately judge the exact distance or the exact height of the lip.
The edge gets fuzzy.
Right. And if you misjudge the lip of a wall by 2 centimeters when you're moving at 3 meters a second, you miss the grab. You fall. So they found that while standard point cloud noise was necessary for sim to real, artificially blurring the edges actively degraded the parkour performance.
That is such a subtle but crucial detail. You need crisp edges to calculate a high dynamic trajectory.
Absolutely.
Okay, so they built the PHP framework, They densified the data with motion matching, trained the hybrid student, tackled the latency. How did it actually perform? Let's talk about the results.
The results were statistically dominant. They tested their PHP policy against a few different baselines. The first baseline was a standard velocity tracking approach.
Which is basically standard reinforcement learning without the motion matching reference data.
Exactly. And it could handle small obstacles, stuff around 36 centimeters high. But as soon as the wall got taller, it completely failed.
Why did it fail?
The paper notes that the standard RL policy just tried to step on everything. It treated every obstacle like a big staircase. It never really understood how to effectively use its arms to pull his body weight up.
Which works fine for a curb, but not a wall that comes up to your chest.
Right. Then they tested an uncomposed data baseline. This one used the human motion clips, but without the motion matching logic to intelligently stitch them together.
So they just dumped the raw clips into the training buffer.
Yes. And it failed heavily on the transitions. The robot would literally run up to a wall and just stop. It didn't know how to seamlessly switch its internal state from walking mode to climbing mode.
Because it hadn't learned that specific connective tissue during training.
Exactly.
And then, of course, there's their method, PHP.
Which achieved a 100% success rate on many of the tasks. And on the hardest task, the 1.25 meter high wall, it hit a 95% success rate.
95% is incredible for something that dynamic. And the hardware demos in the video supplement really back it up. They showed a 60-second continuous run.
Yeah, that was impressive.
The robot wasn't resetting between obstacles. It was just running, vaulting, landing, running, climbing, rolling over boxes.
It genuinely looked like an athlete. And did you catch the part about the mirrored scenarios?
Oh, yeah. Break that down, because that felt like a huge proof of generalization.
It really is.
Yeah.
So in the training data, let's say the reference trajectory for a cat vault always shows the human leading with their left foot. But out in the real world, depending on the robot's stride length and exactly where it started its run, it might arrive at the box needing to lead with its right foot.
So it's on the wrong foot compared to the animation data.
Right. A rigid, purely imitation-based system would stutter there, or try to awkwardly stutter step to get back to the left foot and probably crash.
But this one didn't.
No, because the policy was trained with so much diversity thanks to that densification process, the robot just autonomously adjusted. It recognized the mirrored state and seamlessly executed a right-footed vault, even though the primary reference was left-footed.
That's amazing. It's not just blindly replaying a tape. It's improvising based on the tape.
That is a perfect analogy.
Yeah.
It understands the physical intent of the motion, not just rote pixel mimicry.
You know, the thing that really stood out to me watching the footage is just the sheer physicality of the robot. We are so used to seeing humanoids move very gingerly.
Static stability.
Yeah. Very careful, slow steps.
Yeah.
This G1 is just throwing itself at walls. It feels like a massive shift in philosophy for the field.
It absolutely is a shift.
Yeah.
We're moving humanoids from being passive walkers to active athletes. And while parkour might sound like a fun niche YouTube demo, the real-world implications are huge.
Because the real world is incredibly unstructured.
Exactly. If you want to deploy a humanoid into a disaster zone or a collapsed building or even just a messy construction site, it can't always just politely walk around an obstacle. Sometimes a pathway is blocked by debris.
And a robot that can only walk is stuck. It fails the mission.
But a robot that can vault over a fallen pipe or pull itself up onto a loading dock can keep working.
It totally changes the topology of the world for the robot. Suddenly an obstacle isn't a dead end, it's just a path you have to go over.
Yes. And the fact that they achieved this level of dynamic agility on a relatively low-cost platform like the Unitree G1, using only onboard depth sensors, no expensive LiDAR, no pre-mapped environments, it proves that this control strategy is actually viable for wide deployment. It's not just $1 million lab trick.
And I think it also really validates the hybrid approach to AI development. Right now, there's a huge trend where people just want to throw massive end-to-end foundation models at every robotics problem.
Just scale the transformer and hope it figures out physics.
Exactly. But this paper clearly says, hold on a minute.
It argues that we don't necessarily need a giant end-to-end GPT for motion. By using classical structure techniques like motion matching to organize the data, and then using targeted learning algorithms to execute it, you get much better results.
With less data and less compute.
Right. It proves that domain structure still matters. We shouldn't just throw away decades of knowledge about animation, kinematics, and control theory.
We don't replace the old techniques, we supercharge them with modern learning.
Precisely. Motion matching provides the strategy, the form, and the reinforcement learning provides the execution, the torque, the balance, the micro-corrections.
So, to sum it up, we now have a robot that can run, jump, and climb better than most humans. It uses video game tech to learn from sparse data, and it uses reinforcement learning to overcome the conservative nature of pure imitation.
And it does all of this vision only, at 3 meters a second.
It's an incredibly impressive piece of research. It really feels like that agility gap is closing faster than anyone expected.
It is. I think the immediate next step for this line of research will be applying PHP to even more complex dynamic environments.
Like what?
Maybe irregular shifting terrain,
Yeah.
moving obstacles, or ideally executing these parkour maneuvers while carrying a payload.
Carrying a payload while catvaulting. Now that is a mental image. Here is your Amazon package. Sorry, I had a wall run over your Honda Civic to deliver it.
Hey, it's efficient delivery.
It is. Before we wrap up this deep dive, I want to leave you with a final thought to mull over. We talked earlier about the torque burst problem and how the robot had to learn to fully commit to the jump.
Right. The reinforcement learning prioritized the outcome over just looking correct.
Exactly. Function over form. It makes you wonder, as we start integrating these high agility, success-driven policies into general purpose robots, how much of that aggressive physicality is going to bleed over into everyday tasks?
What do you mean?
Well, if a robot learns that the absolute most efficient way to open a stuck door is to just shoulder check it, because the RL reward only cares about the door opening quickly, are we going to see robots moving with this kind of intense, explosive efficiency in our homes and workplaces, the kind of movements we usually only associate with elite athletes or, honestly, predators?
That is a fascinating point. We might end up sharing spaces with machines that are surprisingly intense.
Robots with swagger. And maybe a little too much kinetic energy for comfort. Definitely something to think about as these systems leave the lab. Thank you for joining us for this episode of AI Paper Podcasts. If you want to read the full methodology, check the link to the paper in the description. We will catch you on the next deep dive.
See you then.